students, welcome to another lecture in environmental modeling and simulation. Today I am going to demonstrate how to solve a simple one-dimensional ODE system using open source R. The software R was initially designed for statistical analyses, much like SAS and other non-open source tools that were prevalent at that time in the market. However, R has evolved over the years to become a very powerful programming and data visualizing tool. So today, however, we are only going to use R for ODE, and very briefly I'll show you how to plot the results that we get by solving ODE. The package we'll be using is dsolve. To follow along with this lecture, I encourage you to install R, which is freely available on your computer or your laptop. There's also a way to use R online, but then the number of analyses you're allowed to do online is limited per day, so that can be an issue. R is available for use on Ubuntu, on Linux-based other OS, on Windows, and also on Mac. So your operating system should not be an issue. Let's get started. So this is how the interface of R looks like when you use it along with RStudio. If you use standalone R, you will get just the command window, which is what we see here on the bottom left side. On typically the top right corner of RStudio, which is a graphical user interface for R, you will get the plots, and once we start plotting our code, you will see plots come here. And at the bottom right, I have opened up the help section to show you, in case you need help from R regarding a particular code or a package, you can access the help here. A simple way of accessing help is to type a question mark and write the code that you are looking up. And in this case, since we are solving ordinary differential equation, we look up ODE. Now, since ODE is already open, it is saying that it cannot find ODE. Let's look at the error message. When I typed question mark ODE, this should have refreshed itself, the bottom right part of the screen. However, it gave me a feedback saying no documentation for ODE in specified packages and libraries. You could try question mark ODE. So if I use question mark ODE, basically I'm asking R to find all kinds of possible help that it can, that matches the string of characters I have written here. However, the error message that I've gotten here, which is that in specified packages and libraries, it is unable to find ODE, tells me that I need to load the package in which ODE, the solver for ordinary differential equations, exists, which, as I know myself, is dsolve. Let's try following this instruction of R, which is to use double question mark ODE. Now, when I do that, R looks across all the packages that have a command which resembles ODE. So here we have 6 linears, 6 different packages and models which use ODE, and I'm interested in dsolve because that's the package which has ordinary differential equation solvers for us. So in case you're starting in R and you have never used dsolve, the first step that you will need to do is to install the package. And you can use the command install packages, or if you are using RStudio, you can even use some of the buttons here to install your package. The package that we need to install is dsolve. Since I have already installed it, I'm not going to run this particular line of the command. Like in MATLAB, we use %sign to denote that the particular line or particular phrases behind that follow %sign are comment. In R, we use the hashtag. So since the package is already installed, I have put a hashtag to denote this is a comment. I'm not going to install dsolve. However, I'm going to load the library, which is telling the R that I need to use this particular package. And let's see what happens if I look for ODE results. Okay, it still cannot find. So I guess I'll have to click here. And then it opens the documentation related to dsolve package, where I can find examples on how to use dsolve for solving ODE. One of the amazing things about R is that the documentation is very well done. Alrighty. So to give you an example of how to use R for solving ODE, ordinary differential equations, we are going to use one-dimensional system of logistic equation. So solving logistic equation using R. Now, the code that I want to use is called ODE, and this code is a part of dsolve package. So what we can do is we can go to the ODE, we can go to the dsolve package and look for how ODE is used to write the code. And typically the format which, and this is a, seems like a very big document. Since R has very good documentation, we can just look up how ODE solvers work on our documentation website, and this is already open here for you. And you can see that in general, this is your R documentation for ODE. In general, the format of using the command ODE follows this: ODE y comma times comma function comma parameter comma method, and then you close the bracket. Now, our documentation will tell you clearly what y times function and parameters are. Y is the initial state. So let's try writing this. First, we will write the initial stage. So ODE initial state n0, comma. Then we are going to write times. So times is the time duration for which I want the model to be solved. So let's just call it times. And then let's define times and n0. So in this case, let's start with n0. Let's say I'm starting with 4, or let's say 1 organism. And the time duration is from 0 to 30. All right, we have defined the initial starting quantity, we have defined the time duration. And now the next we need to define the function that we are solving for. So now we need to define the function. Unlike MATLAB, where at the end of every sentence of the code, you need to put some information telling MATLAB that, hey, the sentence of the code has ended here. In R, you just need to press the enter and move on. So let's write the function func. We can give it a better name. Let's call it logistic. One thing I have learned over the many years is that with R, be very careful how you name your codes, how you name your parameters. And R is not very good at distinguishing the similarity between capital alphabet and small alphabet, small letter. So be very consistent in which alphabet is capitalized in your names and which is not. Okay, so we're defining a function called logistic, and the code for defining the function is function. First, we need to tell R what will be the inputs of this function, and the input would be times, would be your parameters, and you would also be inputting the variable n. And then inside the curly bracket, we'll define the function. So our function is dn by dt. You can use any name. It can be just d capital N. I prefer dn by dt. There are some rules around how to name your variables or your functions so that the R does not get confused. With practice, you will learn that. So we are defining logistic function. So parameters. So first parameter, params 1, which will be the growth rate, multiplied by n, multiplied by bracket, 1 minus n divided by second parameter, which will be the carrying capacity. So now we need to define the parameters. Now parameters, we are defining it by using params, which is a short form of parameters, and it's just a set of numbers. So here we can define it like so: R is equal to, let's say, 0.4 and comma, and this is my growth rate, and then K is the carrying capacity, let's call it 100, and this is my carrying capacity. So always a good idea to be consistent and clear about what you're writing in the code. It's quite possible that some undergraduate student will make use of the codes that I write. So I like to keep the comments so that people know what I'm talking about. For example, here it would be a good idea to write initial n. And there are some people can be very careful about how they write comments. Very consistent and very careful. Time delay, time interval. Alrighty. So we have defined the parameters. We have defined, so if I run this code, just this part of the code, where I'm defining the parameters R and K, and then I want to check that my R has understood what I'm saying. So to check that, let's try with the round brackets and let's see what happens. When I try round bracket, R does not know what I'm talking about because the syntax is wrong. Let's try square bracket. Square bracket R knows that the first input that I've given in this set is R is equal to 0.4. All right, so this is working. And we have defined the function. So if we look at this function, we have defined the logistic function and we have informed the R about what our function looks like here in this line. We need to tell R how to return, what to return when we are defining the function. And if we look at the package dsolve, you can see examples here on how to define the function. First thing you need to do is talk about the input, which they have defined, then the list of parameters, then you write the equations here, and then you tell R what do you want R to return. So in this case, I want R to return a list of dn by dt. So we need to write here return list dn.dt. Okay, this should work. Now my function is ready. So the function is called logistic. We are coming back to ODE, what the format for ODE looks like. And if you remember here, in our documentation, which is excellent documentation of R packages, we have defined the time interval, we have defined the initial values, the function, and the parameters. So now we are ready. We are ready to solve. Now as we need to write parameters here. So if you look here, after the function, we define the parameters. In our case, the parameters are called params, which is short for parameter. Let's give this a name. So let's call it solution is equal to. Notice that I have been using a single equal sign to assign values. Another alternative in R is to use this particular collection of symbol. I find it easier to use equal. Notice that I'm putting a space before and after the equal sign, but that's not a requirement in R. It's just it looks more neat. Okay. Let's run this and see what happens. This also needs to be cut, just so that you know. So we are ready to run our solution. We are ready to run our ODE function. Make sure you run the library dsolve. So R knows we are using the library. And here there's an option of running all the code, so we can use that function. Or you can just control A and then run all the code. There we go. So now we have run this ODE. Let's see the output. One way to see the output in R is to just type the name and press enter. And look, R has given us some values, time, and dn by dt. So now let's try to plot time versus, not dn by dt, sorry, n. It has integrated. Let's plot n versus time diagram. In R, the code is very simple. First, I'm writing time, which will be on x-axis, and then n, which will be on y-axis. I can also give it a color. So let's use the color blue. R has a wide range of colors that you can try. So you see here, we have gotten our solution, time on x-axis, n on y-axis, here in the plot. Now I use Ubuntu for my personal work and not Windows. Like this is RStudio on Windows. Typically my graphs come on the top right, not bottom right. So this is new for me as well. Okay, perfect. So you notice it is showing you a very good graph on how logistic function will behave. Initially, there is an exponential increase in n, then almost a linear increase, followed by a very good logistic S-curve. So overall, it looks like an S-curve. Now, what happens? What happens if we are starting with a different initial condition? If it's truly a logistic system, and our initial number is not a small number close to 0, but a number that is, let's say, 200, which is twice the carrying capacity. What happens when we start with this? How does our diagram look like? So let's remove this diagram, this plot, and let's run the code again. And you see a very nice quick decay until the n value reaches 100. Let's draw all the possible conditions together. So let's say NO1 is the first initial condition is 200. NO2, the second initial condition, let's make it 100, which we know is the carrying capacity. And then NO3, let's make it a small number like 10, which we know should show a nice exponential growth at the beginning. For each of these starting conditions, a simple method could be to have different solutions and plot them all together. There's a cleverer way of doing this, but since this is not in our course, we can just add more lines to our code. Now each time I run this ODE for different initial value, I'm saving the solution under a different name. Sol 1, Sol 2, Sol 3 are different solutions. Okay. I also need to correct here to make sure that R knows. So this one will be, the blue line would be for n corresponding to N01. Let's give it gray color corresponding to the second initial value. And let's give this the color red. Let's try orange. Okay. Let's try running and seeing what happens. We can clear the plot here before we proceed. Okay, notice one thing, that my y-axis where the n is plotted ranges from 100 to 200, which is the range that was appropriate for the first graph. And then the other graphs are not very visible, not very clear. And the reason for that is that I need to redefine the y limit. R can be a very powerful graphing experience, especially if we use, for example, if we use ggplot2. And now all three have plotted together. And you can see the red line is showing an S-like but slightly more flattened because the initial n value is not 1 but 10. If I reduce it to 1, let's see how it looks. Let's remove this graph. See, very nice initial S curve. In the gray, you get a nice straight line because 100 at n is equal to k, which in this case is 100, is a fixed point. It's a stable fixed point. Notice when we start at an initial value of n less than the fixed point, which is a stable fixed point, eventually the value of n reaches the fixed point, and when we start at a much higher value, it again reaches the fixed point. Now in this, we can modify our plot. Now notice that the time appears to be discrete. So we can make the time appear not discrete by defining the line type. And if I'm not mistaken, there's a very simple way of telling R that, hey, I want the plot to use lines instead. There you go. So you can make a plot that looks like this. Now rest of them unfortunately are still showing up as points. So let's try to indicate to R that I need all the plots to not show me the dots but to show me the line. As I said, R was basically designed to be a statistical software. However, it does a very good job with plotting and with solving ODE. This code will be available to you for using and for your own experimentation with this lecture. Now students, as you notice that the gray line is very light, the orange line is also not very visible. So we can do something fun, we can have fun here. R has a very good palette of colors. So if you go online and just look up R colors, you'll find a lot of them. And they are both in the hexa system and also with numbers and names. So let's see. I hope that these ones, oh yeah, look, they have names. So black is a good color to use. It's a bright one, dark blue, and gold. Let's use these three colors. Blue was a good one, but let's go to dark blue. Instead of gray, let's use black. Instead of orange, let's use gold. You can also ask R to play around with the line thickness. Okay, I hope this contrast is clearer. Anyway, these are aesthetics you can play around later with. But this is how we solve a very simple 1D system using DSolve, using the ODE in R. Now, in MATLAB, I told you about ODE 45, which uses fourth order Runge-Kutta method. Here also, you can define the kind of solver you need. R is very flexible like that. So here, for example, these are the different methods that are commonly used. The default is LSOTA, but you can use ODE 23 and ODE 45, which have variable step size, which is at every step, R decides what the step size should be. Okay. All right, students, I hope this was a good introduction to how to use R to solve a very simple ODE. The example I gave you is of logistic equation, which is a very simple, very popular, commonly used one-dimensional system. You can use exactly the code that I gave you with minor modifications to run 2D, 3D, and multiple dimensional models on R. Now, it is quite possible that as you increase the number of models, your computer's computing power might be a limitation. R is not really designed for very heavy computational work, but I have seen people use it for doing some really good work. I hope the introduction I gave you was helpful. Now, when it came to visualizing our result, remember sky is the limit. Since this was a one-dimensional model, I only plotted n versus time, but it is also possible to draw phase portrait by plotting dn by dt versus n at every step for every given time. And in multidimensional models, you can very easily make phase portraits using R. In the next lecture, we are going to look at bifurcations, which is what happens when the parameters change value. Does the behavior of the system remain the same or does it change? See you in the next lecture.